Have you ever looked up at the night sky and felt that tug of wonder, the kind that makes your breath catch just a little? For thousands of years, the stars have been more than just distant lights. They've been storytellers, guides, and silent keepers of humanity's deepest mysteries. Every culture, from the ancient Babylonians to the Polynesian navigators, has woven myths around those glittering points, turning them into gods, heroes, and omens. But what if I told you that hidden within those stories are clues, secrets about the universe and our place in it? Today, we're unraveling 35 of these celestial myths, peeling back layers of legend to reveal startling truths about how the stars shaped history, science, and even the way we see ourselves. Think about it, long before telescopes or space probes, people relied on the stars to explain the unexplainable. A comet wasn't just a ball of ice and rock. It was a portent of doom or a divine messenger. The Milky Way wasn't a galaxy. It was the spilled milk of a goddess or a path for wandering souls. These myths weren't just flights of fancy. They were humanity's first attempts to make sense of the cosmos. And here's the fascinating part: many of them hold surprising grains of scientific truth. The same stories used to teach morality or predict harvests also encoded observations about planetary motion, star cycles, and even eclipses. So why does this matter now? Because these myths are more than relics of the past. They're a mirror, reflecting how humans have always sought meaning in the vast, indifferent universe. As we dive into these 35 legends, from the Greek tales of Orion to the Aboriginal Dreamtime stories, written in the stars, you'll start to see the night sky differently. You'll notice how a myth about the Pleiades might hint at ancient astronomical knowledge, or how a Norse saga about the sun's disappearance could describe a real solar event. This isn't just about stargazing, it's about uncovering the hidden dialogue between science and storytelling, a conversation that's been going on since the first human looked up and wondered. Ready to decode the secrets of the stars? Let's begin. One of the most persistent myths about our closest celestial neighbor is the idea that the moon has a permanent, dark side, a region forever locked in shadow. But here's the reality. Every inch of the lunar surface basks in sunlight at some point. The confusion starts with a mix-up between dark side and far side. While it's true that we only ever see one face of the moon from Earth, a phenomenon called tidal locking, that doesn't mean the other half is eternally night-shrouded. Thanks to a subtle wobble in the moon's rotation known as libration, sunlight actually sweeps across all its regions over time. Centuries ago, astronomers like Galileo peered through early telescopes and noticed something peculiar. The moon's surface seemed to shift slightly, revealing glimpses of terrain beyond its usual profile. This wasn't magic, it was libration in action. Picture a dancer rotating slowly but swaying just enough to show you flashes of their back. Over a month, this gentle rocking lets sunlight reach even the moon's polar craters, which some ancient cultures once imagined as bottomless pits of eternal darkness. Modern missions like NASA Lunar Reconnaissance Orbiter have confirmed it. There's no true dark side, only areas temporarily shaded during the moon's day-night cycle. What's fascinating is how this myth took root. Before the space age, artists and writers dramatized the moon's hidden hemisphere as a forbidden zone think age. G. Wells' lunar caves or fantastical maps from the 1700s depicting monstrous landscapes. Even today, pop culture clings to the phrase dark side, thanks to its ominous allure. But science tells a different story, a world where light dances equally, just out of our view. Next time you gaze up, remember, the moon keeps no secrets from the sun. Those shimmering stars might look like tiny sparks flickering in the night, but here's the truth: their dance isn't about size at all. Ancient astronomers like Ptolemy believed the stars themselves were trembling, suspended in celestial spheres that vibrated like plucked strings. Some cultures even saw it as the gods winking or spirits stirring. But science reveals a far simpler explanation. Earth's own atmosphere is the master illusionist. Every glimmer, every color shift is just light wrestling its way through layers of turbulent air. Picture a straw in a glass of water, how it appears to bend at the surface. That's refraction, the same trick our atmosphere plays on starlight. as beams travel hundreds or even thousands of light years only to hit Earth-swirling pockets of warm and cold air. They get twisted, scattered, and split into fleeting flashes. Even the steadiest star becomes a disco ball by the time it reaches your eyes. And the closer a star is to the horizon, the worse the distortion gets, since its light has to cut through even thicker slices of atmosphere. That's why Sirius, the brightest star in our sky, often puts on the most dramatic light show, blazing white one second, then flaring red or blue the next. What's wild is how long this mystery endured. For centuries, thinkers argued over whether twinkling came from the star's nature or Earth's interference. It wasn't until telescopes pierced the heavens that astronomers noticed something telling. Planets don't twinkle. Why? Because unlike distant stars, planets are close enough to appear as tiny disks in the sky, not pinpricks. Their broader surface area averages out the atmospheric distortion, giving them that steady glow. Next time you're stargazing, try spotting Venus. It'll hold its light like a calm flame, while the stars around it flicker wildly. Modern observatories bypass this chaos entirely by planting telescopes in space, or using adaptive optics that flex their mirrors 1,000 times a second to cancel out atmospheric blur. But there's poetry in the old myths too. The ancient Greeks weren't entirely wrong. Those celestial spheres were moving, just not the ones they imagined. Every twinkle is proof that even the farthest star is locked in a silent conversation with our own restless planet. The North Star has always held a special place in human imagination, a steadfast beacon guiding sailors across uncharted seas and travelers through trackless deserts. But here's something that might surprise you. Polaris isn't actually the brightest star in the sky, not even close. In fact, it doesn't even crack the top 40. Sirius, Vega, and Arcturus all outshine it by a wide margin. So why does this unassuming star, barely visible in light-polluted cities, hold such legendary status? The answer lies not in its brilliance, but in its perfect alignment with Earth's axis, a celestial pivot point that's made it humanity's most reliable compass for thousands of years. Ancient mariners didn't need Polaris to be dazzling. They needed it to be constant. Unlike other stars that wheel across the sky, Polaris hovers almost motionless above the North Pole, its position varying by less than a degree throughout the night. The Vikings called it Stjarna, the leading star, and relied on it to navigate treacherous Atlantic crossings. Some Norse sagas even describe it as the nail holding up the rotating dome of the heavens, with the other stars tethered to it like threads. Meanwhile, many Native American tribes saw it as the star that does not walk, a fixed point around which the Great Spirit wove the tapestry of creation. The Lakota revered it as Witch-Happy Oangilla, the star at the center, a symbol of stability in a world of change. But here's the twist: Polaris wasn't always the North Star. Thanks to a slow wobble in Earth's rotation called axial precession, the title shifts over millennia. 14,000 years ago, the brilliant Vega, now the fifth brightest star, marked true north. And in another 12,000 years, it will reclaim that role. Even Polaris's current reign is temporary. It's only been within 1 degree of the poles since the Middle Ages. That impermanence adds another layer to its mythos, a reminder that even the most unchanging landmarks in our lives are part of a grander cosmic dance. So the next time someone points to Polaris as the brightest, you'll know the real story. Its power isn't in its light, but in its quiet, unwavering presence, a lesson that sometimes the most important guides aren't the loudest voices, but the ones we can always count on. Across countless cultures, streaks of light tearing through the night sky were seen as stars plummeting to earth, divine signs, stolen fire, or souls escaping the heavens. The Greeks called them Diopetes, literally fallen from Zeus, while medieval Europe whispered they were angels cast out of paradise. But these so-called falling stars have nothing to do with stars at all. They're cosmic crumbs, specks of dust and rock, some no larger than a grain of sand, blazing into oblivion as they slam into our atmosphere at over 150,000 miles per hour. Think of Earth as a windshield on an interstellar highway. Those fleeting flashes, just bugs hitting the glass. Most meteoroids, the technical term for these space particles, are debris left behind by comets, icy wanderers that shed material as they loop around the sun.
When our planet plows through these dusty trails, we get meteor showers. The Perseids in August, for instance, come from comet Swift-Tuttle, which last passed by in 1992, but left a glittering river of debris along its orbit. Each fiery streak is a piece of that comet vaporizing 60 miles overhead, a farewell fireworks show from an object that might not return for another century. Ancient skywatchers weren't entirely wrong to see meaning in these bursts, though. Roman generals famously altered battle plans after meteor showers, interpreting them as Jupiter's approval or warning. The Perseids coincide with the feast day of St. Lawrence, leading some medieval Europeans to call them the Tears of Laurentius, believing they marked the saint's martyrdom. Science may have revealed the mechanics, but the magic remains. Next time you catch a shooting star, remember, you're watching the last breath of something that may have traveled billions of years just to burn up in your blink. Few constellations have sparked as many varied legends as the Great Bear, that sprawling pattern of stars we call Ursa Major. To the ancient Greeks, these 7 bright points trace the shape of a bear pursued eternally by the hunter Orion, a punishment from Zeus for the nymph Callisto's betrayal. But look across the globe, and you'll find wildly different stories etched in those same stars. The Micmac people of North America saw not a bear but a celestial bear hunt, with the bowl of the Big Dipper as a group of hunters chasing the animal represented by the star Alker. In Hindu mythology, the same stars form the Saptarishi, the 7 sages who guided humanity's earliest wisdom. Their unity so sacred they were placed forever in the sky. What's remarkable isn't just the diversity of these tales, it's how each culture projected its deepest values onto the stars. The Greeks framed the heavens with dramas of love and vengeance, while indigenous narratives often wove the constellation into practical lessons about survival and respect for nature. The Algonquin tribes taught that the Great Bear's position predicted the seasons. When its bowl tilted downward in autumn, it was pouring out the harvest, and when it rose upright in spring, it signaled time to plant. Meanwhile, in ancient China, the same stars formed part of the heavenly bureaucracy, a celestial government where the Big Dipper's handle was the chariot of the celestial emperor. Science offers its own twist. Those close-knit stars are actually light years apart, their connection an illusion of perspective, but that doesn't diminish their power. Whether serving as a cosmic clock, a moral parable, or a divine courtroom, the Great Bear proves one thing: humanity has always turned the sky into a mirror, reflecting back what matters most to those who dare to look up. Astrology's claim that the stars shape our personalities is one of those ideas that feels ancient and intuitive until you trace its origins. The Babylonians didn't invent the zodiac to decode human traits. They created it as a celestial calendar. Those 12 signs, originally just markers to track the sun's path through the seasons. Aries signaled spring planting, Scorpio warned of autumn floods. Personality readings came much later, when Greek thinkers like Ptolemy merged Babylonian astronomy with their own philosophical musings, suggesting planets influenced our temperaments. But here's what often gets lost. Even Ptolemy saw astrology as probabilistic, not deterministic, more like weather forecasting than fate writing. Fast forward to modern science, and the cracks in astrology's foundation are hard to ignore. Studies repeatedly find no correlation between birth dates and personality traits when controlling for biases like the Barnum effect, our tendency to accept vague descriptions as deeply personal. In one famous experiment, people rated generic horoscopes as eerily accurate, even when every participant received the same text. Yet dismissing astrology entirely misses why it endures. Carl Jung offered a compelling middle ground with his theory of synchronicity, the idea that events can be meaningfully connected without direct causation. To Jung, astrological symbols weren't causing personalities, but reflecting archetypes' universal patterns in the human psyche. A Leo's boldness or a Pisces' dreaminess might not come from distant stars, but from shared cultural stories we internalized. This bridge between myth and psychology reveals astrology's real power, not as a cosmic rulebook, but as a mirror for self-reflection. When someone says Mercury retrograde explains their miscommunication, they're not invoking astronomy, they're using celestial metaphor to articulate human experience. That's why the zodiac persists, even among skeptics. It's less about the stars controlling us and more about how we've always used them to tell stories about ourselves. For centuries, the shimmering band arching across the night sky wasn't just a spectacle, it was a story waiting to be told. The Greeks called it galaxias, meaning milky circle, born from the myth of Hera's spilled breast milk as she nursed the infant Heracles. But look beyond the Mediterranean, and you'll find the Milky Way woven into creation myths worldwide. The Maori saw it as Te Ikaroa, the canoe of the sky god Tane, who used its starry hull to haul the heavens into place. The Cherokee envisioned it as the trail of a mischievous dog who scattered cornmeal across the sky while fleeing villagers. Every culture painted it with the brush of their beliefs, yet none guessed the astonishing truth: that hazy river of light is actually our edge on view of the galaxy we call home. Galileo Galilei shattered these myths in 1610 when he pointed his crude telescope skyward. Where others saw a celestial smear, he resolved countless pinpricks of light stars too faint for the naked eye to separate. This revelation didn't just demote the Milky Way from divine pathway to mere stardust, it cracked open humanity's understanding of the universe. Suddenly, the sky wasn't a fixed backdrop with decorative lights, but a dynamic, three-dimensional ocean where Earth was just one island among many. Yet these ancient stories weren't entirely wrong. Polynesian navigators used the Milky Way's structure as a map, steering their voyaging canoes by recognizing dark patches like the Coalsack Nebula, regions we now know are dense interstellar dust clouds. The Inca called these dark constellations, seeing not just the stars but the shadows between them as sacred animals. Modern astronomy confirms their sophistication. The Great Rift dividing the Milky Way isn't a celestial river fork, but a sprawling lane of cosmic debris, obscuring the galaxy's brilliant core from our view. What's poetic is how these myths and discoveries intertwine. The same stars that guided Pacific navigators for millennia are now used by astronomers to trace our galaxy's spiral arms. The spilled milk of Hera, it's actually the combined glow of billions of suns, so distant their light blurs into a luminous mist. Even Galileo's groundbreaking observation was incomplete. He couldn't know we're inside the very galaxy we study, like an ant trying to comprehend the shape of the hill it crawls upon. So next time you gaze at the Milky Way, remember, you're not just looking at stars. You're seeing a tapestry where science and myth share threads, each revealing truths about the cosmos and about ourselves. Few celestial events struck terror in ancient hearts like a solar eclipse, the sun's sudden, inexplicable vanishing act. Babylonian astrologers scoured their clay tablets for patterns, convinced these ominous shadows foretold royal downfalls or impending invasions. In ancient China, eclipse records often coincided with reports of emperors executing astrologers who failed to predict them. The word eclipse itself comes from the Greek eklepsis, meaning abandonment, as if the gods had turned their backs on humanity. But buried beneath the fear was something extraordinary, meticulous observations that would one day unravel the universe's clockwork. Take the Babylonians. Their eclipse logs, etched in cuneiform over 2,500 years ago, weren't just doom-laden prophecies. They were early scientific datasets. By tracking cycles like the Saros, a repeating 18-year eclipse pattern, they could anticipate future events with startling accuracy. One tablet from Uruk even predicts an eclipse within a few hours in 71b. See, a feat requiring generations of skywatchers passing down precise records. Meanwhile, in China, the Book of Documents recounts an eclipse from 2000b. See, so accurately that modern astronomers used it to calculate Earth's slowing rotation. These weren't primitive superstitions. They were the birth pangs of celestial mechanics. Then came Aristotle, whose vision of perfect, unchanging heavens dominated Western thought for centuries. He argued comets were atmospheric phenomena, and that the moon's glow came from its own light, ideas eclipses directly contradicted. When the moon passed before the sun, its jagged edge revealed mountains and valleys, not a flawless sphere. Lunar eclipses cast Earth's round shadow on the moon, proving our planet wasn't flat. Yet these clues were ignored or explained away until Galileo's telescope shattered old dogma. Today, we know eclipses as celestial ballets, their timing calculable down to the second. NASA eclipse maps would make Babylonian scribes weep with joy. Their once feared omens now reduced to tourist attractions. But there's humility in that transformation. Those ancient skywatchers, though wrong about the meaning, were right to stand in awe. Their fear birthed the discipline that now lets us predict eclipses millennia in advance, turning dread into understanding. For nearly 2 millennia, the idea that Earth stood motionless at the center of creation wasn't just a theory, it was doctrine. Aristotle's crystalline spheres, Ptolemy's intricate epicycles, and the Church's divine cosmology all agreed. The sun, planets, and stars revolved around us in perfect, unchanging harmony. This geocentric view wasn't merely incorrect. It was a narrative so deeply embedded in culture, religion, and science that challenging it meant risking everything. Giordano Bruno learned that the hard way when he was burned at the stake in 1600 for heresy partly, for daring to suggest the sun was just one star among countless others. What's often overlooked is how reasonable the geocentric model seemed at the time. After all, we don't feel Earth moving beneath our feet. Watch a sunset, and your eyes confirm the sun is the one descending, not us rotating away from it. Ancient astronomers noted how planets like Mars occasionally looped backward in the sky, a phenomenon called retrograde motion, and Ptolemy's fix was elegant. He proposed planets moved in smaller circles, called deferents, while simultaneously tracing larger orbits around Earth. It was convoluted, but it worked well enough to predict celestial motions for centuries. The math, though cumbersome, became a sacred scaffolding, propped up by the weight of tradition and institutional power. Then came Nicolaus Copernicus, a Polish cleric, who quietly dismantled the cosmos in 1543, with on the revolutions of the heavenly spheres. His heliocentric model wasn't just revolutionary, it was elegant. Suddenly, retrograde motion made sense without contorted epicycles. It was simply Earth overtaking Mars in their shared race around the Sun. Yet Copernicus waited until his deathbed to publish, knowing the backlash would be severe. Even then, his ideas were dismissed as hypothetical tools for calculation, not literal truth. The real tragedy lies in how long truth fought for air. Galileo's telescope revealed moons orbiting Jupiter. Proof not everything circled Earth yet in 1633, the Inquisition forced him to recant. Johannes Kepler's laws of planetary motion showed orbits were ellipses, not perfect circles, further eroding the old cosmology, but dogma dies hard. It took until 1822 for the Catholic Church to lift its ban on heliocentric books, 259 years after Copernicus's death. What's fascinating isn't just the myth's stubbornness, but why it persisted. A sun-centered universe didn't just challenge astronomy, it dethroned humanity from the cosmic center stage. If Earth was just another planet, what did that mean for our divine significance? Today, we know the sun itself isn't central, it's a suburban star in a spiral arm of the Milky Way, which is one of trillions of galaxies. Each layer of this truth has been met with resistance, a reminder that myths aren't just about facts, but about the stories we tell ourselves to feel at home in the universe. Bruno's ashes may have cooled, but the fire he lit still burns in every scientist who dares to ask, what if we're wrong? Black holes have long been painted as the universe's ultimate monsters, cosmic vacuum cleaners, sucking in everything nearby with unstoppable hunger. Science fiction loves this image, from terrifying wormholes to planets spiraling into oblivion, but the reality is far stranger and more subtle. A black hole's power isn't in some supernatural sucking force. It's simply gravity obeying Einstein's rules, warping space-time so severely that not even light can escape once it crosses the event horizon. Think of it less like a vacuum and more like a waterfall. Stand far enough upstream, and the current is gentle. Get too close to the edge, and the pull becomes inescapable. This distinction matters because it reveals how black holes interact with their surroundings. Take our own Milky Way's supermassive black hole, Sagittarius A. Despite its 4 million solar mass heft, stars orbit it safely at a distance, just as planets orbit the Sun. Only material straying within a critical boundary about the distance from Mercury to our Sun gets stretched into a glowing accretion disk before vanishing. Even then, black holes aren't efficient eaters. Most infalling gas gets flung outward in violent jets, a cosmic messy eater spraying food everywhere. The myth of the all-consuming abyss finally met its match in 2019. when the Event Horizon Telescope unveiled the first ever image of a black hole's shadow in galaxy M87. That glowing ring, not a whirlpool of destruction, but light bent by gravity's lens, a precise confirmation of Einstein's predictions. The black hole itself remains invisible, a silent silhouette against its own gravitational echo. What's poetic is how these observations mirror early theoretical work. In 1783, John Michell imagined dark stars, whose gravity trapped light, while Karl Schwarzschild's solutions to Einstein's equations in 1916 laid the mathematical groundwork. Today, we know black holes aren't galactic janitors but cosmic architects. Their mergers sending ripples through space-time, and their jets seeding galaxies with heavy elements. They're less vacuum cleaners and more gravitational lighthouses, beacons, revealing where the laws of physics twist into their most extreme forms. For centuries, the zodiac's 12 neat divisions have felt as fixed as the stars themselves, Aries to Pisces, each assigned its slice of the celestial pie. But crack open an astronomy textbook, and you'll find a plot twist. The sun actually passes through 13 constellations on its yearly journey, not 12. The forgotten member, Ophiuchus, the serpent bearer, a sprawling star pattern wedged between Scorpio and Sagittarius. This isn't some modern discovery. Ancient Babylonians knew about it 3,000 years ago. So why was it cut from the astrological lineup? The answer reveals how human convenience reshaped the heavens. The Babylonians, master sky mappers, originally divided the zodiac into 12 equal 30-degree segments around 700 B. See, not because there were 12 constellations along the sun's path, but because 12 was a sacred number in their base 60 mathematics. Ophiuchus, though crossed by the sun for 18 days each year, didn't fit their tidy system. Faster forward to Ptolemy in the 2nd century AD, who codified astrology as we know it, and the omission stuck. But here's where it gets messy. Earth's wobbling axis, called precession, has slowly shifted the stars' positions over millennia. The zodiac signs, fixed to the seasons rather than the constellations, now lag almost an entire sign behind. Today's Taurus babies were actually born under Aries stars, a fact NASA casually noted in a 2016 blog post, sparking internet panic over changed zodiac signs. Astrologers were quick to dismiss the uproar, pointing out that tropical astrology, the Western system, intentionally ignores the shifting stars, tying signs to equinoxes instead. But the controversy highlights a deeper tension: astrology's symbolic 12-part framework versus astronomy's messy reality. Ophiuchus isn't the only outlier. The sun also briefly grazes the edge of Cetus, the whale. Yet these cosmic truths rarely make horoscope columns. Perhaps the real lesson lies in why we cling to 12 signs at all. 12 divides neatly into seasons, months, and personality archetypes. 13, that's a prime number, rebellious, indivisible, refusing to fit our patterns. From Babylonian priests to modern horoscope apps, we've always preferred a structured sky, even if it means ignoring the serpent bearers slithering through our celestial stories. Venus has long been dressed in Earth's clothes, our so-called twin shrouded in clouds, similar in size and composition, close enough to spark fantasies of verdant jungles and alien civilizations. Early science fiction writers like Edgar Rice Burroughs painted it as a steamy paradise, a swampy sister world teeming with exotic life. Even Carl Sagan, before the space age, speculated about Venusian oceans beneath those reflective clouds. But when humanity finally pierced that veil, the truth was a cosmic gut punch, a scorched wasteland where lead melts on the surface and sulfuric acid rains from skies thick enough to crush submarines. The myth of Earth's gentle twin began unraveling in 1610, when Galileo turned his telescope toward Venus and noticed something revolutionary. It exhibited phases like the moon, waxing and waning as it orbited the sun. This simple observation shattered geocentrism, proving planets circled the sun, not Earth. Yet for centuries afterward, Venus's thick clouds hid its horrors. It wasn't until 1962, when NASA Mariner 2 flew by, that we got our first rude awakening. Temperatures hot enough to vaporize tin, an atmosphere 90 times denser than Earth's, with clouds of sulfuric acid swirling in winds faster than hurricanes. By the time Soviet Venera probes landed in the 1970s, transmitting data for mere minutes before succumbing to the inferno. The fantasy was officially dead. What's fascinating isn't just how wrong we were, but why. Venus and Earth are cosmic siblings born from the same stellar nursery, both rocky worlds with similar gravity. But somewhere along the way, their fates diverged catastrophically. A runaway greenhouse effect turned Venus into a pressure cooker, its oceans boiling away until only a carbon dioxide blanket remained, trapping heat eternally. Those reflective clouds that once fueled dreams of tropical skies, they're the very thing that sealed the planet's doom, bouncing sunlight back to space while trapping infrared radiation below. Yet even this hellscape holds clues to Earth's future. Scientists study Venus like a cautionary fossil, a glimpse of what happens when a climate spiral goes unchecked. Its volcanoes, possibly still active, whisper warnings about planetary-scale tipping points. That's the real twist in Venus's story. It's not our twin, but our mirror showing us a version of Earth where the balance tipped too far. Next time you see Venus glowing serene in twilight, remember, beneath those brilliant clouds lies the solar system's most potent lesson in planetary survival. One of the most recognizable patterns in the night sky isn't a constellation at all, it's a cosmic decoy. The Big Dipper's 7 bright stars feel like a fixed celestial landmark, but they're actually just a small piece of a much larger puzzle. Ursa Major, the Great Bear. Here's the key distinction. Constellations are officially recognized regions of the sky, like countries on a map, while asterisms like the Big Dipper are unofficial star patterns within them. Think of it like spotting the face of a clock in a painting. The clock exists within the artwork, but it isn't the whole piece. This celestial shorthand has deep roots in storytelling. For the Micmac people, the Big Dipper's bowl represented hunters pursuing the bear, the star alker, barely visible to the naked eye, was the small pot they carried to cook their prey. The Iroquois saw the 3 stars in the handle as 3 warriors chasing the bear through the sky each autumn, their hunt mirrored in the seasonal turning of the stars. Meanwhile, in the lore of the Shawnee and other Algonquian tribes, the Dipper's curve held life or death urgency. It was the drinking gourd, a celestial map guiding escaped slaves northward to freedom. The North Star, anchored by the Dipper's pointer stars, wasn't just a navigational tool, it was a beacon of hope woven into spirituals like "Follow the Drinking Gourd." Its lyrics disguised as folk advice but packed with covert directions. What's astonishing is how this asterism's practicality crossed cultures. Ancient Greek sailors used it to find Polaris, just as Underground Railroad conductors taught freedom seekers to trace a line from the Dipper's lip to the North Star. Even today, the Dipper's position acts as a celestial clock. When its handle points east at dusk, spring is coming. When it dips low in the northwest, winter is near. That's the magic of asterisms. They're humanity's shared blackboard, where myths, survival strategies, and scientific observations all get scribbled across the same stars. So next time you spot those 7 familiar points, remember, you're not just seeing a spoon in the sky. You're glimpsing a crossroads where navigation, history, and legend all converge. Dark matter has a branding problem. Its name makes it sound like some Inkai, light-swallowing substance straight out of a horror movie. The truth is far stranger. We call it dark not because it's black or invisible to our eyes, but because it refuses to play by the usual cosmic rules. Unlike stars, planets, or even interstellar dust, dark matter doesn't emit, absorb, or reflect light in any way we've detected. Yet its gravitational fingerprints are everywhere, warping the very fabric of the universe in ways visible matter alone could never explain. The first clue came in 1933, when Swiss astronomer Fritz Zwicky noticed something bizarre about the Coma galaxy cluster. By measuring how fast galaxies orbited the cluster's center, he calculated their collective mass, and the numbers didn't add up. The visible stars and gas accounted for only a fraction of the gravity needed to hold the cluster together. Zwicky, never one for understatement, called the missing mass Dunkel Meteori dark matter, and declared it a cosmic glue keeping galaxies from flying apart. Most of his peers dismissed the idea as speculative, but Zwicky's ghost got the last laugh. Fast forward to the 1970s, when astronomer Vera Rubin uncovered even stronger evidence while studying spiral galaxies. Stars at the edges of galaxies like Andromeda were orbiting just as fast as those near the center, defying Newton's laws. If only visible matter existed, those outer stars should have been moving slower, like Pluto crawling around our solar system compared to Mercury's sprint. Instead, they zipped along as if yanked by some unseen hand. Rubin's galaxy rotation curves became the smoking gun. Every galaxy we've studied since is embedded in a vast, invisible halo of dark matter, stretching far beyond its luminous edges. Here's where things get really weird. Dark matter isn't just hiding in plain sight, it's architecting the universe. Simulations show that without its gravitational scaffolding, galaxies would never have formed in the first place. Ordinary matter, the stuff we're made of, was too busy ricocheting off photons in the early universe's plasma to clump together efficiently. Dark matter, indifferent to light's push and pull, quietly gathered into dense webs, creating gravity wells where atoms could finally settle down and spark stars. Yet after nearly a century of searching, we still don't know what dark matter is. Is it a sea of undiscovered particles, like WIMP or actions, streaming through your body right now? Could it be primordial black holes formed in the universe's first second? Or does gravity itself behave differently at cosmic scales, rendering dark matter an illusion? Every experiment, from underground particle detectors to gravitational lensing maps of distant galaxies, inches us closer to the answer. Until then, dark matter remains the ultimate cosmic ghost story, a shadowy protagonist shaping everything we see while leaving no trace of itself. The next time you look up at the Milky Way, remember, the stars are just the glitter on the surface. Most of our galaxy's weight is in the darkness between them, pulling strings we're only beginning to understand. The full moon has always worn a mask of mystery, blamed for sleepless nights, erratic behavior, even spikes in crime. Emergency room nurses swear they see more patients during lunar peaks, and police departments sometimes staff extra officers when the moon is bright. The term lunatic itself comes from the Latin luna, reflecting the ancient belief that the moon could sway the human mind. But when scientists actually crunch the numbers, a surprising pattern emerges. The moon's pull on human behavior might be nothing more than a trick of the light. Take the persistent myth linking full moons to increased birth rates. For centuries, midwives whispered about lunar tides triggering labor, a notion Aristotle lent credence to by claiming the moon influenced bodily fluids just as it did ocean waves. Yet modern studies of millions of births show no statistical bump. The same goes for crime decades of police reports from cities like New York and Los Angeles reveal no measurable correlation between lunar phases and violent acts. Even emergency room admissions, when adjusted for weekends and holidays, show no lunar effect. So why does the myth persist? The answer lies partly in something called confirmation bias. We remember the chaotic nights when the moon was full, but forget the dozens of equally busy shifts under a crescent or new moon. The werewolf legend offers another clue. Stories of humans transforming under moonlight appeared across medieval Europe, often tied to folklore about the moon's power to reveal hidden truths or unleash primal instincts. In reality, these tales might have roots in medical conditions. Porphyria, a rare disease causing sensitivity to light and erratic behavior, could explain historical werewolf cases, especially since attacks were often reported during bright moons, when victims ventured outside. The moon didn't create monsters, it simply illuminated them. But before we dismiss lunar influence entirely, consider this: the moon does affect life on Earth, just not in ways pop culture suggests. Coral reefs time their spawning to lunar cycles, and certain nocturnal animals hunt more actively under bright moonlight. Even some human sleep studies show slightly reduced deep sleep during full moons, though the mechanism remains unclear. The moon's real power isn't in driving madness, but in shaping the rhythms of nature and, perhaps, in the stories we tell to make sense of our own unpredictability. After all, it's easier to blame the silver disk in the sky than admit how little control we sometimes have over our chaos. The stars seem like permanent fixtures, eternal pinpricks of light anchoring the night sky in place. But here's the cosmic reality. Every star you see is in motion, drifting across the galaxy like ships on a dark ocean. We don't notice their movement because human lifespans are mere blinks in astronomical time. Yet over centuries, these subtle shifts add up. Take Barnard's star, a humble red dwarf just 6 light-years away. It's the fastest-moving star in our sky, sprinting at about 140 kilometers per second. If you could watch it over a human lifetime, you'd see it crawl a distance equal to the width of the full moon. Not much until you realize that in just 8,000 years, it'll shift by more than a degree, altering the shape of its constellation forever. Ancient skywatchers unwittingly documented this stellar dance. Egyptian astronomers around 3000 B.C. recorded constellations that no longer match our own. Their depictions of gods and animals, etched into temple ceilings, show stars in positions subtly but unmistakably different from today's arrangements. The Big Dipper's handle, for instance, appears more bent in their records, a detail modern astronomers confirmed by calculating how those stars have moved over millennia. Even Polynesian navigational charts, passed down orally for generations, describe star paths that have since curved slightly off course. These aren't errors, they're time-lapse snapshots of a dynamic universe. Proper motion, the term for a star's apparent drift across our sky, reveals a deeper truth. Constellations are temporary. The celestial artwork we take for granted is more like a sand mandala, destined to scatter. 100,000 years from now, Orion's belt will loosen, its stars stretching into a shape our ancestors wouldn't recognize. Sirius, the brightest star in our sky, is barreling toward us at nearly 8 kilometers per second, meaning future civilizations will see it glow even brighter before it eventually veers away. This fluidity challenges the very idea of fixed celestial patterns. The Greeks named constellations based on myths that mattered to them, but those stories were always written in vanishing ink. The North Star wasn't always Polaris, and it won't be forever. The stars we use to navigate, to mark seasons, to tell stories, they're all passing through, leaving no permanent address in the sky. Next time you trace the outline of a constellation, remember, you're catching just one frame in a billion-year film, where every star has its own path, and no 2 generations see quite the same sky. For centuries, poets and philosophers have described the universe as a silent void, a realm of perfect, soundless emptiness stretching between the stars. Even today, movies reinforce this idea with scenes of eerie quiet in deep space. But here's the cosmic twist. The universe is far from silent. We just couldn't hear it until now. Thanks to NASA groundbreaking sonification projects, we've discovered that black holes hum, galaxies pulse, and nebulae resonate with frequencies that would make even Pythagoras, the ancient Greek who dreamed of the music of the spheres, drop his lyre in awe. The irony is delicious. Pythagoras theorized that celestial bodies produced harmonies as they moved perfect, mathematical tones too sublime for human ears. Medieval scholars expanded this into the concept of the harmony of the world, linking planetary orbits to musical intervals. For all their poetic intuition, they missed a key truth: space does sing, just not in the way they imagined. Instead of ethereal melodies, we get the guttural groans of colliding black holes, the metallic ping of neutron stars, and the ghostly hiss of plasma waves, all translated into audible sound through the magic of modern science. Take the Perseus galaxy cluster. In 2003, astronomers detected pressure waves rippling through its superheated gas in the aftermath of a supermassive black hole's explosive tantrums. These waves, oscillating once every 10 million years, were far too low for human hearing, but when NASA scaled them up by 57 octaves, the result was chilling, a deep, resonant hum, like the lowest note on a piano played underwater. It's not music in the traditional sense, but it is proof that even the emptiest corners of space vibrate with hidden rhythms. Then there's the infamous black hole at the center of galaxy M87, the first ever photographed. By sonifying the light echoes from its accretion disk, shifting X-rays to high notes and radio waves to bass scientists created an uncanny soundscape. The result, a chorus of whale-like moans layered over a pulsing drone, as if the cosmos itself were sighing. It's a far cry from Pythagoras' celestial lyre, but somehow more profound. The universe doesn't compose tidy symphonies. It improvises, screeches, and rumbles like a cosmic jazz ensemble. What's revelatory about these sonic experiments isn't just their strangeness, but their utility. By translating data into sound, researchers can detect patterns invisible to telescopes. A flicker of gamma rays becomes a chime. A ripple in gravitational waves morphs into a drumbeat. This isn't just art, it's a new language for decoding the cosmos. So next time someone calls space a silent abyss, tell them to listen closer. The universe has been performing an avant-garde concert for billions of years. We're only just tuning in. In the late 1800s, telescopes across the world turned toward Mars, and one man saw something no one else could: a sprawling network of canals crisscrossing the red planet. Astronomer Percival Lowell became obsessed, mapping hundreds of these phantom lines in intricate detail, convinced they were artificial waterways built by an advanced civilization struggling to survive on a drying world. His sketches, published in lush, hand-drawn atlases, showed geometric precision straight as railroad tracks, intersecting at oases he claimed were hubs of Martian commerce. The public went wild. Newspapers breathlessly reported on Lowell's discoveries, and H.G. Wells spun them into the War of the Worlds, where thirsty Martians eyed Earth's oceans with envy. But there was one problem: the canals didn't exist. Lowell's eyes, or more likely, his mind, had played tricks on him. Peering through the blur of Earth's turbulent atmosphere, his brain connected dim surface patches into straight lines, a phenomenon called pareidolia, the same quirk that makes us see faces in clouds. Even in his era, many astronomers failed to replicate his observations, yet Lowell's myth persisted for decades, fueled by a perfect storm of scientific optimism and colonial-era thinking. If we built canals, surely an older civilization would too. The myth only shattered in 1965, when NASA Mariner 4 flew past Mars, snapping 21 grainy photos that revealed nothing. No canals, no cities, just a cratered wasteland under a thin pink sky. What's fascinating isn't just Lowell's error, but how it mirrored humanity's hopes and fears. His canals emerged during the peak of terrestrial engineering projects like the Suez and Panama Canals, era-defining feats that reshaped continents. To Victorians, Mars became a cautionary tale, a warning of what Earth might become if resources ran dry. Wells inverted this in War of the Worlds, casting Martians not as noble engineers, but as desperate invaders. Both versions, though, shared a core belief that Mars was a mirror. Modern missions have revealed a planet far stranger than Lowell dreamed. Dry riverbeds and mineral traces prove water once flowed freely, but any canals were carved by ancient floods, not alien hands. Even today's sharpest orbital cameras show no trace of Lowell's geometric grids. Yet his legacy lingers in our language. The word Martian still conjures little green men, not robotic rovers. Mariner 4 didn't just debunk a myth, it forced us to confront a deeper truth. We've always painted other worlds with brushes dipped in our own ambitions, fears, and lonely curiosity. The real Martians, it turns out, were the stories we told about ourselves all along. We've all heard the ominous phrase, when the stars align, a shorthand for fate conspiring, disasters looming, or cosmic checks finally cashing in. The 2012 Mayan apocalypse scare ran with this idea, warning that a rare planetary alignment would trigger earthquakes, solar flares, or even a polar shift. But here's the cold, hard truth of orbital mechanics. Perfect alignments don't exist. Not in our solar system, not in any system. The universe doesn't do straight lines. The illusion starts with perspective. From our vantage point on Earth, planets sometimes appear to cluster in the sky, like cars momentarily stopped at the same traffic light. But this is just a trick of angles. Imagine standing in the center of a circular racetrack with runners strewn along different lanes, some close, some far. From your position, two might briefly seem side by side, even though they're separated by vast distances. That's how planetary alignments work. During the much-hyped 2012 event, the planets were actually scattered across hundreds of millions of miles, with no gravitational influence on one another, let alone Earth. Dig deeper, and the myth crumbles further. Each planet in our solar system orbits the Sun on its own tilted plane, like layers of a misaligned wedding cake. Mercury's path is cocked 7 degrees relative to Earth's, while Pluto's, yes. It's still a planet in our heart's slants a dramatic 17 degrees. These orbital inclinations mean that even if you could freeze all the planets in a line from the sun's perspective, they'd still be staggered vertically, never meeting in a neat row. The last time the solar system's major bodies even came close to alignment was in 561 B.C., and even then, the alignment was more like a loose scatterplot. The Mayan prophecy panic revealed something fascinating about human psychology, though. Ancient skywatchers did track planetary motions meticulously. The Dresden Codex, a Mayan astronomical text, accurately predicts Venus's cycles, but they saw them as celestial omens, not doomsday triggers. Modern sensationalism twisted their nuanced calendar into apocalyptic clickbait. Meanwhile, NASA scientists spent 2012 debunking tidal force math on live TV, patiently explaining that the combined gravity of aligned planets would still be weaker than the moon's pull on a single ocean wave. So why does the alignment myth persist? Because chaos is terrifying, and the idea that the universe might sometimes snap into order, even destructively, offers a strange comfort. It's the same reason we see faces in clouds or patterns in static, but the cosmos doesn't work that way. The real magic isn't in imaginary straight lines. It's in the beautiful, untidy choreography of orbits forever almost, but never quite meeting. Those shimmering curtains of green and violet lighting up polar skies have been misunderstood for centuries as mere reflections, sunlight bouncing off Arctic ice or high-altitude crystals. But the truth behind the northern lights is far more violent and beautiful. This celestial light show isn't a reflection at all. It's the aftermath of a cosmic battle raging 60 miles above our heads, where Earth's magnetic shield wrestles with the sun's fury. Every aurora begins with a solar tantrum. When the sun hurls charged particles our way, a torrent called the solar wind, they don't just sail smoothly into the atmosphere. Instead, they slam into Earth's magnetosphere, a teardrop-shaped force field generated by our planet's molten core. Most of these particles get deflected, but some sneak through near the poles, where magnetic field lines funnel them downward like water swirling down a drain. As these solar invaders plunge toward Earth, they smash into oxygen and nitrogen atoms, exciting them like neon signs. The result, oxygen glows green or red, while nitrogen flashes blue or purple, nature's own plasma screen stretching across the sky. Long before science unraveled this process, indigenous cultures had their own profound explanations. The Sami people of Scandinavia saw the aurora as the energies of departed ancestors' souls so vibrant their joy shimmered across the heavens. Some believed whistling at the lights would summon them closer, while others warned that disrespectful behavior might provoke them into snatching you skyward. Inuit legends from Greenland described the aurora as walrus spirits playing ball with a human skull, their movements creating ripples of color. One haunting Algonquin tale tells of celestial hunters lighting the sky with torches as they pursued a giant bear, their fiery tracks staining the night. What's striking is how these myths mirror scientific reality in unexpected ways. The Sami's dancing ancestors echo the way solar particles actually spiral along magnetic field lines, creating the illusion of undulating curtains. Inuit stories about the lights making crackling sounds, once dismissed as folklore, were vindicated in 2012, when researchers confirmed auroras produce audible claps caused by electromagnetic disturbances. Even the feared sky abductions might have roots in a real phenomenon. Auroral storms can induce electrical currents strong enough to trigger hallucinations in rare cases. Modern science hasn't stripped the aurora of its magic, it's added new layers. Satellites now track solar storms like weather forecasts, while photographers capture the lights in resolutions our ancestors couldn't imagine. Yet standing under those swirling colors still feels transcendent. Whether you see them as proton collisions or ancestral whispers, the northern lights remain one of Earth's greatest wonders, proof that even our planet's most dazzling spectacle is just a shadow of larger forces at play. It's one of the most universally accepted facts about our planet. The moon's gravity pulls on Earth's oceans, creating the rhythmic rise and fall of tides. But here's the twist: the moon doesn't work alone. Our sun, that distant, blazing star, plays a crucial role in the tidal drama, shaping the tides in ways that often go unnoticed. The truth is, tides aren't a simple tug of war between Earth and the moon. They're a cosmic collaboration, with the sun's gravity stepping in to amplify or soften the moon's influence depending on the alignment of these celestial bodies. Take spring tides, for example, those especially high and low tides that have nothing to do with the season and everything to do with alignment. When the sun, moon, and earth form a straight line during full and new moons, their gravitational forces combine like teammates, pushing in the same direction. The sun's pull, though weaker than the moon's at this distance, adds an extra nudge to the tidal bulge, making high tides taller and low tides shallower. Conversely, during first and third quarter moons, when the sun and moon form a right angle with Earth, their gravitational forces partially cancel each other out. This creates neap tides, the quiet, understated cousins of spring tides, where the difference between high and low water is far less dramatic. Galileo, ever the revolutionary thinker, actually got this one spectacularly wrong. In his quest to prove heliocentrism, he argued that tides were caused by Earth's motion around the sun, a theory that conveniently ignored the moon's role entirely. To him, the sloshing of the oceans was proof of Earth's movement, like water sloshing in a moving bucket. He dismissed the moon's influence as superstition, a misstep that left his tidal theory fatally flawed. It wasn't until Newton's law of universal gravitation that the moon's true role, and the sun's supporting act, was finally understood. The sun's tidal influence is subtle but undeniable. While its gravitational pull on Earth is nearly 200 times stronger than the moon's, its sheer distance dilutes its tidal force. That's why the moon, despite being smaller, exerts a stronger tidal grip. It's much closer, allowing its gravity to create a sharper difference in pull between one side of Earth and the other. But the sun's contribution is still significant enough to modulate the moon's work, turning the tides into a dynamic interplay of forces rather than a one-sided affair. Even today, tidal patterns reveal hidden clues about our place in the solar system. Ancient navigators noticed these rhythms long before the physics was understood, using them to time harbor entries and predict fishing conditions. Modern oceanographers study tidal discrepancies to map seafloor topography, since underwater mountains and valleys subtly alter tidal flows. And astronomers, peering at distant exoplanets, now look for tidal distortions as hints of oceans, or even moons orbiting far-off worlds. So the next time you watch the tide roll in, remember, it's not just the moon's hand at work. The sun, that silent partner in the sky, is lending its weight to the dance, a reminder that even in the vastness of space, everything is connected. Galileo may have missed the moon's role, but his mistake teaches us something vital. The universe is always more complicated and more collaborative than it first appears. Every few months, headlines scream about an incoming supermoon, a looming celestial giant that's supposedly bigger, brighter, and somehow more dangerous than a regular full moon. Social media fills with ominous warnings, earthquakes, tidal chaos, even strange behavior. But strip away the hype, and the reality is far less dramatic. A supermoon is only about 14% larger in the sky than an average full moon, a difference so subtle most people wouldn't notice without side-by-side photos. That's like holding up a basketball next to a soccer ball. Technically one's bigger, but from a distance, the distinction blurs. The myth of supermoons as disaster triggers has roots in a basic misunderstanding of scale. Yes, the moon's orbit is elliptical, bringing it closer perigee and farther apogee from Earth each month. At its closest approach, a supermoon can be roughly 30,000 miles nearer than its most distant point. But in cosmic terms, that's a trivial shift. The moon's average distance is 238,000 miles, so even a close supermoon is still astronomically far away. To put it in perspective, if Earth were the size of a basketball, the moon at its closest would be a tennis ball 23 feet away, and at its farthest, just 26 feet. You'd hardly sense the difference walking past them. What about those supposed earthquake links? Seismic data tells a different story. After the devastating 2011 Tohoku earthquake in Japan, conspiracy theorists insisted it was triggered by that year's supermoon, which occurred 2 weeks later. But scientists quickly pointed out the flaw. If the moon's gravity could spark quakes, we'd see spikes in seismic activity every 2 weeks during regular tides, not just during supermoons. The truth is, the moon's tidal forces do stress Earth's crust by about half a millimeter. That's less than the natural expansion of rocks from daytime heating. Major quakes originate miles underground, where lunar influence is laughably weak compared to the grinding of tectonic plates. Even the supermoon effect on tides is overstated. While a supermoon's slightly stronger pull can elevate tides by an extra inch or two, that's dwarfed by routine coastal flooding from storms or seasonal winds. Fishermen and sailors have known this for centuries. They track local weather patterns far more closely than lunar phases. The real danger isn't the moon. It's the human tendency to weave cosmic explanations for random tragedies. So why does the supermoon myth persist? Part of its sheer spectacle. Photographers love shooting the moon near the horizon, where atmospheric refraction and foreground objects create an illusion of enormity, the infamous moon illusion that has nothing to do with actual proximity. And let's face it, super sells. A regular full moon doesn't grab clicks like a celestial apocalypse, but next time you see those alarmist headlines, remember, the universe operates on scales far beyond our daily worries. The moon's dance with Earth is a delicate, predictable rhythm, not a harbinger of chaos. Just a quiet reminder of how gracefully the cosmos moves, with or without our drama. Hollywood loves painting space as a frozen wasteland, a silent void where everything instantly freezes the moment it leaves Earth's atmosphere. But the truth is far more extreme and surprising. Temperature in space isn't just cold. It's a chaotic roller coaster, swinging between blistering heat and cryogenic chills depending on where you are and whether you're in sunlight or shadow. Take Mercury, the solar system's speedster planet. During its long daytime, surface temperatures soar to a scorching 800 degrees Fahrenheit, hot enough to melt lead. Yet just a few feet beneath its sun-baked rocks, or on its night side, temperatures plummet to minus 290 degrees. That's a swing wider than any desert or polar region on Earth. This misconception likely started with Arthur C. Clarke's iconic 2001, A Space Odyssey, where the alien monolith is described as being at absolute zero, the theoretical temperature where all molecular motion stops. It's a gripping image, but it's scientifically impossible in the real cosmos. Even in the deepest voids between galaxies, space never hits absolute zero. The cosmic microwave background, the faint afterglow of the Big Bang, keeps the universe at a baseline of about minus 455 degrees Fahrenheit. That's chilly, but still a few degrees above the ultimate cold. What really defines temperature in space is the absence of air. On Earth, our atmosphere acts like a giant thermal blanket, spreading heat through conduction and convection. But in space, without molecules to carry warmth, objects don't experience cold the way we think of it. Instead, they either roast in unfiltered sunlight or radiate their heat away into the void. The International Space Station faces this daily dance, its sun-facing side fries at 250 degrees, while the shadowed side freezes at minus 250. Engineers use radiators and reflective coatings to manage this brutal swing, a far cry from the simple, freezing space of sci-fi lore. Even spacecraft tell this tale. Apollo missions had to carefully rotate their lunar modules like chickens on a rotisserie to avoid baking one side while the other iced over. Meanwhile, the Parker Solar Probe, which flies closer to the sun than any human-made object, survives 2,500-degree heat with a carbon shield that reflects 99% of incoming radiation. The lesson: space isn't just cold or hot, it's both, often at the same time. Next time you hear someone call space a deep freeze, remember, it's more like stepping into an oven while holding a block of dry ice, with nothing in between to soften the extremes. The idea that the universe stretches on forever has fueled both scientific speculation and spiritual awe for centuries. Poets imagine endless galaxies, philosophers ponder infinite existence, and even modern astronomers casually toss around the word infinite when describing cosmic scales. But here's the catch: we don't actually know if the universe is boundless. What we can measure is the observable universe, a sphere around us roughly 93 billion light-years across, containing all the light that's had time to reach Earth since the Big Bang. Beyond that, the cosmos might go on indefinitely, or it might curve back on itself like the surface of a globe. The truth hinges on a deceptively simple question: Is the universe flat, curved, or something even stranger? Current cosmological observations suggest the universe is very close to flat, meaning parallel lines would never meet, and the rules of Euclidean geometry hold true. This flatness comes from a delicate balancing act in the early universe. A tiny deviation one way or the other would have led to drastic curvature. But very close isn't the same as perfectly. Imagine standing on a vast prairie. The ground might seem flat to your eyes, but you're actually standing on a planet that's undeniably round. Similarly, our measurements might just lack the precision to detect the universe's subtle curve. If space is slightly hyperbolic, like a saddle, or spherically, like a balloon, it could still be finite but unimaginably large, with light eventually looping back to its starting point if you traveled far enough. This isn't just abstract math, it echoes ancient intuitions. Hindu cosmology, for instance, describes a cyclical universe where creation and destruction repeat in vast cosmic cycles called kalpas, each lasting billions of years. The Vishnu Purana compares these cycles to the alternating breaths of the divine, an infinite rhythm of expansion and contraction. Modern physics flirts with similar ideas. Some models suggest a cyclic universe where big bangs occur repeatedly, while others propose a multiverse where our cosmos is just one bubble in an endless froth of spacetime. Yet even if the universe is infinite, there's a haunting limit to what we'll ever know. Due to the accelerating expansion of space, light from regions beyond the observable universe will never reach us, their photons stretched too thin by cosmic inflation. Those distant realms are forever hidden, making infinity not just a physical question, but a philosophical one. Are there copies of you out there in an endless cosmos? Does space truly go on forever? Or is it a closed loop too vast to perceive? For now, these mysteries linger at the edge of science and myth, reminding us that some questions about the universe aren't just about finding answers, they're about learning how to ask better ones. Ask any child to draw the sun, and they'll reach for a yellow crayon without hesitation. Even ancient Egyptians depicted their sun god Ra with golden skin, sailing a fiery bark across a turquoise sky. But here's the cosmic joke. The sun isn't actually yellow. It only appears that way because Earth's atmosphere acts like a celestial Instagram filter, bending and scattering its light until we see a warmer version of the truth. In reality, our sun is a dazzling white star, a fact you'd instantly recognize if you could see it from the vacuum of space, where no air distorts its glow. This color deception starts with a phenomenon called Rayleigh scattering, the same trick that turns clear skies blue. Sunlight contains every color of the rainbow, but as those wavelengths plunge through our atmosphere, shorter blue and violet rays get bounced around like pinballs, leaving longer red, orange, and yellow wavelengths to dominate the direct beam we see. During sunrise and sunset, when sunlight slants through the thickest layer of atmosphere, this filtering becomes extreme, transforming the sun into a blazing orange orb. But at high noon, when the sun sits directly overhead and its light takes the shortest path through the air, its true white nature becomes more apparent to the naked eye. The ancient world's golden sun myths weren't entirely off base, though. Solar spectroscopy analyzing sunlight's component wavelengths reveals something poetic. While the sun emits most intensely in the green part of the spectrum, our eyes blend all these wavelengths into white. It's like staring at a spinning top painted with every color. At full speed, it appears colorless. Egyptian artists may not have understood optics, but they captured an essential truth about perception. Their golden Ra wasn't a scientific error. It was an homage to how the sun feels warm, life-giving, and radiant in a way that white laboratory lights could never replicate. Modern science confirms this duality. Satellite images of the sun, unfiltered by Earth's air, show a crisp white disk. Yet even astronauts describe sunlight flooding their spacecraft as having a faint golden quality, proving how deeply human vision is wired to interpret warmth through an atmospheric lens. So next time you squint at the noonday sky, remember, the sun's true color is hidden in plain sight, masked not by cosmic mystery, but by the very air that lets us live long enough to gaze upward. It's a reminder that sometimes, the universe's greatest illusions are the ones we breathe. The sight of astronauts floating effortlessly inside the International Space Station makes it easy to assume they've escaped gravity entirely, like mythical beings stepping beyond nature's laws. But here's the reality that defies every Hollywood moonwalk. There's no such thing as zero gravity in orbit, not even close. What astronauts experience is microgravity, a subtle dance of forces where gravity's pull is very much present. It's just being cancelled out in the most elegant way possible. Picture the ISS not as a place free from gravity, but as a cosmic tightrope walker in perpetual freefall. Earth's gravity at that altitude is still about 90% as strong as it is on the ground. The station and everyone inside it are constantly plunging toward the planet, but with a crucial twist. They're also moving sideways at over 17,000 miles per hour. This speed creates a perfect balance, where their fall curves to match Earth's curvature. The result, they never hit the ground, endlessly missing the planet like a baseball thrown so fast it loops the globe. That's microgravity, not the absence of gravity, but the art of falling with style. Compare this to Apollo-era moonwalks, where Hollywood got almost everything wrong. Films often show astronauts bouncing in slow motion as if underwater, limbs waving dramatically with each step. The truth was far stranger. Lunar gravity is 1/6 of Earth's, weak enough to let astronauts hop like kangaroos, but strong enough to keep them grounded unless they chose to leap. Watch Neil Armstrong's actual footage, and you'll see deliberate, almost tiptoe steps, his body never floating uncontrolled. That's because the moon's gravity, though diminished, still exerted enough pull to anchor him. The real magic of microgravity reveals itself in everyday moments aboard the ISS. A drifting water blob isn't defying gravity. It's falling at the exact same rate as the station around it, creating the illusion of weightlessness. Even the famous footage of astronauts somersaulting in midair is a testament to this equilibrium. They're not floating. They're falling in perfect sync with their environment. This misunderstanding has deep roots. Early sci-fi writers imagined space as a realm where gravity simply stopped beyond a certain height, like stepping off an invisible cliff. Even Newton, though he unraveled gravity's math, couldn't have envisioned orbital mechanics so precise that falling could feel like flying. Today, we understand that gravity never vanishes, it's the frame of reference that shifts. The ISS is proof that sometimes, the most extraordinary phenomena aren't about breaking nature's rules, but learning to move with them in ways that still leave us breathless. One of the most breathtaking images ever captured by the Hubble Space Telescope wasn't just a scientific marvel, it became a cultural touchstone. The pillars of creation, those towering tendrils of gas and dust in the Eagle Nebula, looked like cathedral spires sculpted from starlight when revealed in 1995. But for years, a haunting rumor swirled among astronomers and space enthusiasts alike. What if these cosmic monuments had already been obliterated by a supernova shockwave, and we just hadn't seen it yet because light from their destruction hadn't reached us? The idea clung to the public imagination, turning those ethereal columns into ghosts beautiful, but possibly long gone. Then, in 2014, Hubble did something extraordinary. It revisited the Eagle Nebula with sharper optics, and the pillars were still standing. Not just intact, but glowing with new details, delicate tendrils of gas that hadn't been visible before, and young stars flickering within the dust like embers in smoke. Here's the cosmic irony. Those 7,000 light-years between us and the Eagle Nebula mean we're seeing the pillars as they looked 7 millennia ago. Yet their survival in Hubble's update suggests they've weathered the universe's chaos far longer than anyone guessed. This revelation mirrors an ancient theme, the myth of the phoenix, the legendary bird that dies in flames only to rise anew. Cultures from Egypt to China wove variations of this tale, always centered on destruction birthing renewal. The Eagle Nebula embodies this cycle on a galactic scale. Those pillars are being eroded stellar winds from newborn stars, slowly blowing them apart, but in their dissolution, they're seeding the next generation of suns. Hubble's newer images even show a mysterious, blue haze around the pillar's edges, likely the scorching glow of material being vaporized and recycled into space. The real magic lies in what we can't yet see. The same forces sculpting the pillar's radiation, stellar winds, gravity's tug mean they won't last forever. Some estimates give them another 100,000 years, a blink in cosmic time. But their inevitable demise isn't an end, it's a transformation. Just as the phoenix's ashes fuel its rebirth, the pillar's dust will collapse into new stars, new worlds, perhaps new life. That's the ultimate lesson written in those swirling gases. In the universe, destruction and creation are two sides of the same coin. The pillars of creation aren't just a sight to behold, they're a celestial clock, ticking toward rebirth. That iconic Pink Floyd album title, The Dark Side of the Moon, etched itself into pop culture as a symbol of mystery, secrecy, and the unknown. But here's the twist. The moon's so-called dark side isn't actually dark in the way most people imagine. It's not a shadowy realm of perpetual night, nor is it some alien no-go zone. The truth lies in a simple cosmic quirk, tidal locking. Our moon rotates at the same rate it orbits Earth, meaning we only ever see one face of it. That far side, the one Pink Floyd made infamous, gets just as much sunlight as the side we know. It's not dark in the sense of being unlit. It's just dark to us because we've never seen it from Earth without the help of spacecraft. China's Chang'e 4 mission shattered this myth in dramatic fashion in 2019, when it became the first spacecraft to land softly on the lunar far side. The images it sent back weren't some eerie, shadowed wasteland. They showed a sunlit landscape eerily similar to the near side, just with a lot more craters. The real challenge wasn't darkness, but communication. Without a direct line of sight to Earth, the mission relied on a relay satellite called Queqiao, parked in a special orbit to bounce signals back home. This technological feat was a far cry from the album's psychedelic gloom. It was a triumph of precision engineering, proving the far side isn't some forbidden zone, just a place that's harder to phone home from. What's fascinating is how this myth took root. Before space-age photography, astronomers could only speculate about what lay beyond the moon's visible edge. Some imagined lush valleys hidden from view, while others like Pink Floyd evoked a more ominous vibe. Even the term dark side carries a double meaning. It's not just about light, but the unknown. The band leaned into this mystique, weaving themes of madness and isolation into their music. Yet science paints a different picture. The far side's rugged terrain, free from the vast lava plains that smooth out the near side, holds clues to the moon's violent past. Its thicker crust and strange magnetic anomalies hint at a history of colossal impacts, a story written in rock and dust, not shadows. So why does the myth endure? Because it taps into something primal, our fear of the unseen. From ancient maps marking uncharted territories with "Here be dragons," to modern sci-fi tropes of hidden lunar bases, humans have always projected their anxieties onto the unknown. The far side of the moon is the perfect canvas for those fears, a place close enough to see yet just out of reach. But thanks to missions like Chang'e 4, that canvas is being filled in, one crater at a time. The real dark side of the moon isn't a place of monsters or mysteries, it's just another piece of the cosmos, waiting to be understood. And in a way, that makes it even more extraordinary. Those twinkling points of light we call stars might all look white to the naked eye, but peer closer, and you'll uncover a universe awash with color-fiery red giants, searing blue supergiants, and golden dwarfs flickering like cosmic embers. Take Betelgeuse, the ruby-red shoulder of Orion, burning at just 3,500 degrees Celsius, so cool its glow resembles a dying campfire compared to our sun's white-hot blaze. Then there's Rigel, Orion's opposite foot, radiating an intense blue at 12,000 degrees. Its light so energetic it could tan your skin from 800 light-years away. These hues aren't just celestial decoration, they're cosmic thermometers, revealing a star's temperature, age, and destiny in vibrant brushstrokes across the void. Ancient cultures saw these colors long before telescopes, weaving them into elaborate systems of meaning. Chinese astronomers divided stars into 5 elemental categories tied to the Wu-Xing philosophy: blue for wood, red for fire, yellow for earth, white for metal, and black for water. Betelgeuse's ruddy glow marked it as a fire star, a celestial omen of warmth and transformation, while Sirius's piercing white light signaled metal's sharp, unyielding nature. The Dogon people of Mali named Sirius the Red Star. possibly referencing its companion star Sirius B's reddish glow during rare atmospheric conditions, linking its color to agricultural cycles and spiritual renewal. Even the Greeks described Mars as fiery and Venus as wan, their color distinctions shaping myths of war and love. What's astonishing is how these pre-scientific observations aligned with later discoveries. The redder a star, the cooler and often older it is, like Betelgeuse, bloated and nearing supernova. Blue stars burn hot and fast, their fuel spent in cosmic seconds compared to our sun's middle-aged glow. The medieval Persian astronomer Al-Sufi even noted color variations in his star charts, though he lacked the physics to explain them. Today, we understand stellar colors through spectroscopy, which splits starlight into rainbows to reveal chemical fingerprints. A star's hue depends on its surface temperature. Following the same principle as a heating element, warm metal glows red, hotter turns yellow, and white-hot blazes blue. But here's the catch: our eyes often betray us. Under dark skies, most stars appear white because our night vision relies on rod cells, which are terrible at detecting color. It's only when comparing stars side by side, or through telescopes, that their true shades emerge. Urban light pollution washes out these subtleties, leaving modern skywatchers with a palette far duller than their ancestors enjoyed. That's why photographs of star clusters like the jewel box in Crux dazzle us. They unveil sapphire, topaz, and garnet pinpoints our unaided eyes can't perceive. The next time you gaze at the night sky, remember, those seemingly monochrome stars are a riot of hidden color, each hue a chapter in a story of nuclear fusion, cosmic time, and humanity's endless quest to read the universe's fiery language. Whether viewed through the lens of Wu Xing or Wien's displacement law, the message is the same: the stars were never just white. We simply needed to learn how to see them. For centuries, Earth was considered a cosmic anomaly, the lone oasis in a vast, lifeless desert of space. But the discovery of exoplanets has shattered that illusion, revealing thousands of worlds nestled in the so-called Goldilocks zone, where temperatures are just right for liquid water. Take Kepler 442b, a rocky planet orbiting a star 500 light-years away. It receives about 2/3 the sunlight Earth does cooler, but still potentially habitable. Or consider the 7 Earth-sized planets circling TRAPPIST-1, a dim red dwarf, 3 of which orbit squarely in that temperate sweet spot. These aren't science fiction, they're real places, each with its own unique balance of heat, light, and chemistry that could in theory support life as we know it. The irony is that this revelation echoes a heresy punishable by death in the 16th century. Giordano Bruno, the renegade monk burned at the stake in 1600, dared to suggest that the stars were suns like our own, each with their own inhabited worlds. His vision of an infinite universe teeming with life was deemed blasphemous, a threat to Earth's divine uniqueness. Yet here we are, 4 centuries later, with telescopes like Kepler and tests proving Bruno's intuition startlingly prescient. The difference, where Bruno speculated, we now have data, hard evidence that Earth is just one of many potential Goldilocks planets in a galaxy brimming with possibilities. What's fascinating isn't just the existence of these worlds, but their staggering diversity. Some, like Kepler 162f, orbit sun-like stars in near-Earth conditions. Others, like Proxima Centauri b, cling to red dwarfs in tight, tidal-locked orbits where one side bakes in eternal daylight, while the other freezes in endless night. Then there's K218b, a super-Earth with water vapor in its atmosphere, hinting at oceans beneath hydrogen-rich skies. Each of these planets rewrites the old assumption that habitability requires an Earth twin. Life, it turns out, might thrive in environments we once thought lethal around dim stars, in thick atmospheres, or even beneath icy crusts warmed by tidal forces, like Jupiter's moon Europa. The myth of Earth's singularity wasn't just scientific hubris, it was a reflection of human solipsism. Ancient cultures, from the Greeks to the Mayans, imagined their gods had crafted the cosmos uniquely for them. Even Copernicus, who dethroned Earth from the center of the universe, couldn't shake the idea that our planet held some privileged status. Modern astronomy offers a humbler perspective, with estimates suggesting there could be 40 billion Earth-sized planets in habitable zones across the Milky Way. The real question isn't whether other Goldilocks worlds exist, it's how many of them might be whispering secrets we're only beginning to hear. Bruno's final words before the flames took him were reportedly, "Perhaps you pronounce this sentence against me with greater fear than I receive it." Today, that fear has inverted. The more we find these distant cousins of Earth, the more wondrous and unsettling the cosmos becomes. Not because we're alone, but because we're almost certainly not. The universe hasn't just made room for us, it's built countless other rooms, each waiting for its story to be told. The idea that the moon might be hollow sounds like a plot ripped straight from a B-movie, an ancient alien megastructure masquerading as a celestial body. In the 1970s, this wild theory gained unexpected traction when Apollo seismometers recorded something strange. After lunar modules were deliberately crashed into the surface, the moon rang like a bell for over an hour. Conspiracy theorists pounced, declaring this proved the moon was a hollow shell, perhaps even an engineered artifact. Even Hollywood couldn't resist. Films like Moonfall later spun this into doomsday scenarios where our hollow satellite harbored apocalyptic secrets. But here's what seismic data actually reveals. The moon isn't some cosmic gong. It's just really, really good at carrying vibrations. Those prolonged quakes, called moonquakes, have a simple explanation. The moon's geology is nothing like Earth's. Without water, wind, or tectonic activity to erode its surface, the lunar crust is bone dry and fractured, littered with rubble from billions of years of meteor impacts. When vibrations travel through this fractured, porous material, they don't dissipate quickly like they would on Earth, they bounce and echo, like sound waves in a cathedral. Apollo-era seismologists knew this, but the nuance got lost in sensational headlines. Modern reanalysis of that data, combined with insights from missions like NAS, a lunar reconnaissance orbiter, paints a clearer picture. The moon has a core, mantle, and crust, just like Earth, only colder, quieter, and far less geologically active. The hollow moon myth also stumbles on basic physics. If the moon were hollow, its mass wouldn't match the gravitational pull that literally moves Earth's oceans. Tidal forces depend on the moon's density being consistent with a rocky body, not a tin can. Even the moon's moment of inertia, a measure of how mass is distributed, aligns with a solid interior. When China's Chang missions mapped the moon's subsurface with ground-penetrating radar, they found layers of basalt and breccia, not hollow chambers. What's fascinating isn't just the science debunking this myth, but why it persists. The moon's strangeness, its eerie silence, its stark landscape. Its role as Earth's silent companion makes it a perfect canvas for our wildest speculations. From H.G. Wells' The First Men in the Moon to modern conspiracy forums, we've projected our anxieties and fantasies onto its cratered face. But the truth is more awe-inspiring than fiction. The moon isn't a hollow relic. It's a time capsule, preserving 4.5 billion years of solar system history in its dust. Every quake, every impact scar whispers secrets about planetary formation, cosmic collisions, and the violent youth of our corner of the galaxy. So next time you hear someone claim the moon rings because it's hollow, set the record straight. That echo isn't proof of an alien workshop. It's the sound of a world frozen in time, a monument to the forces that shaped us all. And really, isn't that stranger and more beautiful than any sci-fi trope? Einstein's famous declaration that nothing can outpace light seems like one of those unshakable rules of the universe, a cosmic speed limit etched into the fabric of reality itself. At first glance, the math backs it up. Accelerating any object with mass to light speed would require infinite energy, a clear dead end. But dig deeper, and the story gets slippery. Quantum mechanics and theoretical physics have chipped away at this dogma, revealing loopholes that even Einstein himself might have raised an eyebrow at. Take quantum entanglement, for instance, that eerie phenomenon where two linked particles instantly mirror each other's states, no matter how far apart they are. On paper, this seems to flout light speed, as information appears to teleport between them faster than a photon could travel. But here's the catch. No actual thing is moving between those particles. It's more like flipping two coins light years apart and finding they always land on the same side. Spooky, absolutely. A violation of relativity, not quite. Then there's the Alcubierre warp drive, a concept that sounds ripped straight from Star Trek's engineering manuals. Mexican physicist Miguel Alcubierre proposed in 1994 that instead of moving a ship through space at impossible speeds, you could cheat by bending space itself. Picture a surfboard riding a wave. The board stays still, but the wave carries it forward. An Alcubierre drive would compress space-time in front of a spacecraft and expand it behind, creating a bubble that rides the distortion like a cosmic shortcut. The catch, it requires exotic matter with negative energy density, something we've never observed in nature. Yet recent simulations suggest microscopic warp bubbles might already exist in quantum foam, those fleeting subatomic fluctuations in the vacuum of space. If we could somehow scale this up, a giant if it wouldn't break the speed of light, it would sidestep the problem entirely by redefining the rules of motion. Star Trek's warp core mythology leans into this beautifully, blending science with speculative fiction. The show's warp factor scale isn't just technobabble, it's loosely based on real equations, with warp 1 equating to light speed and higher factors following an exponential curve. But the show's writers took creative liberties, hand-waving the need for exotic matter by inventing dilithium crystals to stabilize the reaction. Real-world physicists chuckle at this, but they also acknowledge how the franchise inspired generations to ponder the boundaries of physics. After all, the line between myth and breakthrough is often thinner than we think. Radio waves were once dismissed as paranoustic nonsense, and black holes were deemed mathematical quirks until we photographed one. The speed of light might still reign supreme for now, but the universe has a habit of surprising us. Whether through entangled particles whispering across the void or theoretical warp bubbles bending the stage beneath our feet, the final word on cosmic speed limits hasn't been written. And that's the real magic, not in breaking the rules, but in discovering how they might bend. Aristotle shuddered at the very idea of a vacuum. Nature abhors empty space, he declared, insisting every crevice of the cosmos must be filled with something. It's a notion that feels almost quaint today, when we know the universe isn't just full, but overflowing with invisible forces that make stars and planets mere afterthoughts. The numbers alone are staggering. Dark energy, that mysterious accelerator of cosmic expansion, accounts for 68% of the universe's contents. Dark matter, the gravitational scaffolding holding galaxies together, makes up another 27%. Ordinary matter, everything we can see, touch, or study in labs, is relegated to a paltry 5%. That's right, the empty void between galaxies is actually a seething ocean of dark energy, while the nothingness within them is laced with dark matter's unseen threads. This revelation turns Aristotle's horror vacui on its head. Where he imagined nature rushing to fill emptiness, we now see a universe where the apparent voids are the main event. Picture a glass of water with a single ice cube. The cube represents all visible matter stars, planets, nebulae, while the water is dark matter, and the invisible forces causing evaporation are dark energy. Our cosmic inventory isn't just lopsided, it's an optical illusion on the grandest scale. Even the blackest patches of space, where not a single star winks, are saturated with these invisible actors. The irony is rich. For centuries, astronomers mapped the heavens by tracing pinpricks of light, assuming the darkness between them was passive and inert. Then came Vera Rubin in the 1970s, studying spiral galaxies and realizing their outer stars orbited too fast, as if gripped by unseen hands. Around the same time, cosmic expansion wasn't slowing as expected. It was accelerating, propelled by some repulsive force now called dark energy. These weren't minor anomalies. They were clues that our universe is more like a shadow play, with visible matter as the fleeting shapes cast by forces we're only beginning to detect. Consider the Bullet Cluster, two galaxy clusters caught in a cosmic collision. When astronomers mapped their mass using gravitational lensing, they found most of it didn't align with the glowing gas. Instead, it lurked in the empty regions, a ghostly footprint of dark matter passing through ordinary matter like a breeze through a screen door. Meanwhile, dark energy's fingerprints are etched into the large-scale structure of the universe, stretching galaxy clusters apart like raisins in an expanding loaf of bread. Aristotle's fear of emptiness wasn't entirely misguided, he just underestimated the universe's creativity. Emptiness isn't absence, It's the stage upon which the cosmos performs its greatest tricks. Every time we peer into the void and call it empty, we're like fish mistaking water for nothingness. The universe doesn't abhor a vacuum. It's too busy filling it with mysteries we're only starting to name. The phrase Big Bang conjures images of a titanic explosion, a fiery detonation flinging galaxies outward like cosmic shrapnel. But here's the twist. The birth of our universe wasn't an explosion at all. It was the rapid unfurling of space itself, a distinction so crucial it reshapes everything we think we know about cosmic origins. Picture inflating a balloon with dots on its surface. As the balloon expands, every dot moves away from every other dot, not because they're being propelled from a central point, but because the fabric between them is stretching. That's the Big Bang, not a bomb going off in space, but space itself awakening and swelling, carrying matter along for the ride. This revelation didn't emerge in a vacuum. In 1927, Belgian priest and physicist Georges Lemaitre proposed his cosmic egg theory, a primordial atom whose disintegration seeded the universe. His ideas were radical for the time, dismissed by some as tinged with religious mysticism. Yet Lemaitre's training in both theology and mathematics lent his work a unique duality. He saw no conflict between science and spirituality, framing cosmic expansion as almost a divine exhale. It's a metaphor that eerily parallels ancient Hindu cosmology, where the god Brahma breathes out universes in cycles of creation and dissolution. The Vedas describe this as pralaya, the rhythmic expansion and contraction of existence, a vision startlingly close to modern theories of oscillating universes or inflationary cosmology. The irony is that the term Big Bang itself was coined dismissively. Astronomer Fred Hoyle, who favored a steady-state universe, used the phrase sarcastically during a 1949 radio debate. It stuck, unfortunately obscuring the nuance of Lemaitre's original concept. What we call the Big Bang wasn't a chaotic eruption, but a structured unfolding, governed by physics we're still deciphering. Cosmic microwave background radiation, the afterglow of that primordial moment, reveals a pattern of tiny temperature fluctuations, like wrinkles in spacetime's fabric, hinting at quantum ripples magnified by inflation. Zoom in on those first fractions of a second, and the story grows stranger. The universe didn't explode into anything, it was all there was, a singularity where the concepts of before and outside lose meaning. Time, space, and even the laws of physics as we know them crystallized during those initial moments. This challenges our everyday intuition, like trying to imagine the north of the North Pole. Yet it's a framework that bridges science and philosophy, echoing both Lemaitre's cosmic egg and Brahma's cyclical breath. Whether through equations or allegory, humanity has always grappled with the same awe, the realization that everything, every galaxy, every atom, every breath we take, is riding the same primordial wave, stretching backward to a moment when all was one. Ancient stargazers saw no divide between predicting royal fortunes and tracking planetary motions to them. The celestial dance was both science and sacred text. For thousands of years, astrology and astronomy were intertwined like twin strands of cosmic thread, with Babylonian priests charting Jupiter's path to forecast harvests, while Egyptian sky watchers aligned pyramids with stars to ensure Pharaoh's passage to the afterlife. Even the Great Library of Alexandria housed zodiacal treatises alongside geometric proofs, their scrolls bearing equal weight. But by the 16th century, this union began fracturing under the weight of new discoveries, and few embodied this tension more vividly than Tycho Brahe, the nobleman-turned-scientist who cast horoscopes for kings while revolutionizing celestial measurements with unprecedented precision. Brahe's observatory at Uraniborg was a temple to contradiction. His brass quadrants and gargantuan sextants could pinpoint star positions within 1 arc minute, an accuracy unmatched until telescopes arrived, yet his notebooks brimmed with the astrological interpretations for patrons like Emperor Rudolf Roman II. When his famous supernova blazed in 1572, Brahe didn't just measure its parallax, proving it lay beyond the moon, shattering Aristotle's immutable heavens. He also penned a manifesto declaring it heralded the fall of Islam and rise of a Nordic savior. This duality wasn't hypocrisy. It reflected an era when science and mysticism shared common language. Astrology funded Brahe's research, just as Kepler later supported his family by casting nativities, even as his laws of planetary motion dismantled the very celestial spheres astrology relied on. The true divorce came with Galileo's telescope, when Jupiter's moons and Venus's phases proved the heavens mutable and Earth not central. Astrology's geocentric foundations crumbled. By Newton's era, the rift was formalized. The Royal Society's fellows mocked horoscopes as star-struck superstition, while almanac writers kept feeding public demand for celestial guidance. Yet traces of the old connection linger in our vocabulary. Consider how disaster comes from the Latin disastra, meaning against the stars, or how influenza was once blamed on malignant stellar influences. What's revealing isn't just how these fields split, but why one became canon and the other folklore. Both sought patterns in chaos astrology through symbolic narratives, astronomy through empirical math. Tycho's legacy reminds us that progress isn't a straight line from myth to truth, but a messy disentangling of ways to know the sky. Today, as telescopes probe exoplanets and algorithms scan ancient horoscopes for statistical quirks, perhaps the divide isn't so absolute after all. The stars still whisper, we've just learned to listen differently. From Babylonian priests tracking omens and star paths to modern astrophysicists decoding black hole echoes, our journey through these celestial myths reveals something profound. Every generation looks up and sees the cosmos through the lens of its deepest hopes, fears, and cutting-edge knowledge. Those ancient stories weren't just wrong guesses, they were stepping stones, each one stretching humanity's imagination a little further toward the truth. When Polynesian navigators charted courses by the Pleiades or medieval scholars mapped astrological houses onto the zodiac, they weren't just spinning tales. They were building frameworks to make sense of a universe far stranger than any of them dreamed. Take the myth of the dark side of the moon, a concept born from our limited perspective, not lunar reality. That simple fallacy held sway for centuries until spacecraft peeled back the curtain, showing how sunlight dances equally across every crater. Or consider how Tycho Brahe's meticulous star charts, meant to empower astrology, accidentally fueled the scientific revolution that would displace it. Every myth we've unraveled tonight, from wandering stars to cosmic alignments, carries this same lesson. The universe doesn't change, but our understanding of it never stops evolving. What's thrilling is realizing how much we still don't know. Dark matter's gravitational whispers, the true nature of black holes, even the possibility of other Goldilocks worlds. These are today's frontier myths, waiting for future generations to decode. The difference now is that we've learned to question our assumptions, to test rather than simply trust. That's the real gift of science, not just answers, but better ways to ask questions. So here's my challenge to you. The next time you hear a celestial fact, whether it's about blue moons, zodiac shifts, or supermassive black holes, dig deeper. Ask where that idea came from, who first believed it, and why. And while you're at it, share your favorite star myth in the comments below. Maybe it's an Aboriginal tale about the emu in the sky, or a Norse legend explaining auroras. Every culture has looked up and woven stories from starlight, and that tradition is alive in all of us. After all, the night sky isn't just a physics classroom, it's the original storybook, written in constellations and cosmic fire. And the best part, we're all still learning how to read it.